symmetries. And we also know that from Noether's theorem, each symmetry there is a conserved current and hence a conserved charge. And we use these conserved charges to label different states as quantum numbers, right? So, but sometimes it happens that although the system respects the symmetries classically, it fails to do so at quantum level. So as a result, so the word identities that are not trivially satisfied anymore. So when you have a conserved current, you will have del mu j mu a equal to 0. But sometimes it happens that this symmetries doesn't survive the journey of quantization, and you have something on the right hand side of del mu j mu uh, equal to equation. So the quantity that appears on the right hand side is called anomaly. So for CFTs, so we previously have seen that there are three word identities mainly. So that concerns with the energy momentum tensors. One is the conservation equation. The second deals with the symmetry of symmetric energy momentum tensors. So that says TAB minus TBA equal to 0. And the third is T mu mu equal to 0, which is the trace equal to 0. So those are the defining properties of the CFTs at classical level. Now we are going to show that when we are dealing with quantum theories, this T alpha alpha equal to 0 no longer vanishes when the theory lives on a curved background. So you have to promote the theory to you have to couple the theory to a curved space-time. So when the theory lives on a curved background, it can be shown that the T alpha alpha is equal to C by 12 times R, where R is the curvature of the background. So there are more than one ways to derive this expression. So what I'm going to do is stick to the simplest one and derive an expression for this anomaly when the theory lives on a slightly curved background. I mean, we don't go far away from flat space. Uh, so yeah, we'll see what we mean by that. Okay, so before going to deriving the anomaly, so let's first understand what it's meant by Weyl transformations and Weyl symmetries. Um, so Weyl transformations are local scale transformations that act directly on the fields without changing its space-time argument. Suppose so the theory depends basically on the metric, the background field, and there are some other fields there might be. So on the Weyl transformation would take the metric up to a local scale factor. So here e to the power omega x is just a convention. You could have written it just omega x. So that's the scaling of the metric, and you can scale the other fields as well with e to the power omega x to the power delta or anything you wish. So delta here is called the Weyl weight of the field phi, suppose. So the Weyl weight of the metric is usually set to 1, and then demanding that the whole theory, the action has to be Weyl invariant, we can determine what is the value of delta. So that depends on the theory, how the matter fields should scale under Weyl transformation in order to make the theory Weyl invariant. So the simplest example of a Weyl invariant theory would be a minimally coupled scalar field in D equal to 2. Here you have just the metric and the scalar field. So here root over, so you can see that here g mu nu goes to e to the power omega x. So g upstairs mu nu will go to e to the power minus omega x, and the determinant will go to uh, determinant of g times e to the power 2 omega x. But as there is a root over g, so there would be only e to the power omega x, and these two factors will cancel. So this is Weyl invariant without scaling the field. So Weyl weight of this scalar fields are here 0. So this is very crucial to d equal to 2. If you, I mean, go to higher dimensions, you can see that this is not going to be while invariant, and you have to add additionally some non-minimal coupling terms with this to make it while invariant. And there you will find that delta is not equal to 0. So delta equal to 0 is very crucial, very characteristic to d equal to 2. This is the characteristic property of d equal to 2. So this is the while invariance of the action. Now we want to know what is the relation of this while invariant theories to conformal field theories. So we have been talking about conformal field theories. So now conformal transformations we have seen to be diffuse that change the metric up to some while factor, right?
We
So
have not
mathematics.
seen this. We have not
Hello,
seen this. Yeah, what I'm saying that we have not really explicitly seen this.
I see.
So I
So
was
so
hoping that you'd actually do this.
uh, okay, so let me explain it. Uh, so the definitions of conformal transformations we have not done, right?
No, we have done it, but I've not explicitly shown. I mean, since we did not do wild transformations, right?
Right.
So there was no reason for me to actually go into this. I mean, why exactly the conformal group is diffeomorphisms modded out by while is something that I did not do.
Okay. So we can we what we know is so the conformal group is the Lorentz group, the Poincare group, right? Plus there is scale transformations, plus there are special conformal transformations. So what we know, the under the Poincare group, the metric doesn't change, and the scale transformations change the metric up to a scale, and so does the special conformal transformations, right? So what it can be shown that the if you act the conformal group on a metric, it will only change up to a while factor. So I maybe should have written a little bit more about this, but
No, but
so
yeah, I guess yeah, you can sort
there
of
is,
give them yeah. So it's sort of maybe intuitively reasonably obvious, but I mean it would have been yeah.
yeah. So if there is
Give
any,
the rest as homework or something like that.
okay,
Okay. Yeah.
okay.
Okay. Okay.
So that would mean the conformal group is diffeomorphism modded out by while. So if you have any questions, please feel free to ask. Okay.
I have a question. Uh,
Yeah.
so like here, like for the demonstration of this anomaly, like you took the trace of the energy momentum tensor. So like we know that in a curved space time, like the energy momentum tensor is covariantly conserved. So the
Right.
other ward entity, that will just remain the same. The ward entity for the conservation of the energy momentum tensor won't have anomalies, right? It's just covariantly conserved. Or is it more
Yeah.
to that?
No, it may have anomalies as well, but those are so I'll come to that. So those are would be those are called gravitational anomalies, and those are corresponding to gauge symmetries. So those has to be gotten rid of.
Okay, okay.
Yeah. So I'll speak a little more about that later on.
Okay, yeah, sure.
Okay. So so we now know that the conformal group is just diffeomorphism modded out by while. So that would mean that if you have a while invariant theory written in a covariant way, it will automatically be conformally invariant. So when you pick up I mean particular coordinate system, or and the covariant theory is while invariant, all you will be left with the transformations that keeps the fields up to a while transformations. And if that doesn't show up in the Lagrangian, it will be conformally invariant. So there is other ways to show this. So suppose in terms of this trace of the energy momentum tensor. So so T mu nu is defined. We can define the energy momentum tensor as the variation of the action with respect to the metric, right? So T mu nu upstairs would be 1 over root over g del s delta of g mu nu. So the variation of the metric would be just root over g t mu nu times delta g mu nu. Now we have seen that under Wild transformations, this the variation, the metric varies by just a scale factor. So delta g mu nu would be some scale omega x times g mu nu. So if you put it back, you will see that delta s equal to the scale factor multiplied by the trace. So now if we want the theory to be invariant under the Wild transformations, the trace of the energy momentum tensor better vanish. And we know that a theory that admits a symmetric conserved traceless energy momentum tensor is a CFT. So if you have Wild invariance in the covariant action, it will be conformally invariant. So this is another way to see it. Okay, so this is so far what we have done is all classical, and and this is the fact that we show going to change when we move on to quantum theories. So the trace no longer remains zero. So let's see how to derive an expression for T alpha alpha. So the setup is we are on a slightly curved background. So that means we are very close to eta alpha beta, if you wish. So and we also assume that T alpha alpha expectation value of T alpha alpha equal to 0 on flat space. Now we are at flat space and T alpha alpha equal to 0. Now we are going to vary the metric slightly, vary a very infinitesimal Wild transformation, and see how this expression of the trace varies. Okay. So now this delta T alpha alpha. So T alpha alpha, if you write it in path integral, would be just integrate d phi to the power minus s times T alpha alpha. That's the expression for path integrals. Now we are going to vary this. So the variation is going to act on the action, and here there is also a G alpha alpha, right? So it's gonna act on two places. So if you vary this, so this T alpha alpha can be written as T alpha beta times G alpha beta. So there would be a delta G alpha beta there, but the delta G alpha beta is just the okay. So here the transformations are like this. So we are starting off with flat space and taking e to the power 2 omega to and scaling it by e to the power 2 omega. Then the metric is going to vary like this, and the upstairs metric is going to vary like this. There would be an extra minus sign. So if you vary it, vary the metric here, then you will get an expectation value of T alpha alpha. So that we have already set to 0. So the only contribution will come from varying this Euclidean action S. Okay. So this S will vary as, again, that we have seen, you can use the definition of energy momentum tensor, and it will vary as root over integration of T to sigma prime root over G delta G alpha beta T beta gamma sigma prime. So if we substitute this back here, we'll get that delta T alpha alpha of sigma is this integration times this expression. So classical, yeah. Is there any question?
In the last slide, shouldn't there be I mean, another division by the path integral where you wrote the average of T alpha alpha?
In the last expression, which one? This one?
Yeah.
Yes. You have to divide it by 1 over g all along in all the steps. That's right. That is right. That is what I probably have not written down. Yeah.
So
That
that will also contain a variation, right?
that will also okay.
No, what exactly do you mean? Are you thinking about sort of uh, I mean normalizing it by the z naught?
Yeah, when we normalize it by a z naught and take the variation, the z naught will also vary, right?
Yeah, I mean, at the moment, I think you can think of these, sort of as being, I mean, as being sort of normalized, basically, in the sense that you're going to think of an endpoint function as the, I mean, exponent. So z, if you wish, so the 0 point function is something which is just the path integral of e to the s, right? E to the minus s. So when you're going to insert something else into it, then yeah, you should just think of that as the I mean endpoint function. So if you have n of these particular operators inserted in, yeah, it's just going to be. Uh, so you're not really thinking about. Uh, yeah, I mean, so you are thinking about this. I mean, the time ordered way that you have been trying to. So okay, so what I mean is, I guess you're not thinking about the normalization of the fields out here in that spirit. But I guess I
Right.
know what you mean. I mean, you're worried about the an extra variation which will come from the del z variation, I guess, right? So that's what you're worried about.
But this the trace of T alpha will contain a G
Yeah, yeah,
alpha
yeah.
beta, right?
No,
So
no,
that variation,
that is yeah, that is there.
Right. But if
if
you only vary, if you yeah. So if you only vary, so there will be 1/g factor here. So if you only vary the z, you will get this factor only. But
Yeah.
here delta g beta gamma you are setting to this, and it will be you will be left with t alpha expectation value again, which you are setting to 0 for flat space. But when you have in the upstairs, you have a T factor extra. So that will lead to this T alpha T beta contact. I mean, this multiplication, right? So that we will show that even if the T alpha of sigma is equal to 0, this product is not equal to 0.
So yes, I guess the answer is in the fact that we are using to actually expand this around flat space, I mean the first part that I mean you brought up,
Yeah.
that is actually equal to 0.
Yes. So
Is that okay?
that
I mean, is that okay, Shivam? Uh,
Yes, sir.
yeah, I mean, if you think that they're yeah, I mean, just try and work this out once, and I think
yes.
if you have any problems, yeah, I mean, just drop us an email, okay? All right,
Okay.
yeah, please go on, Shubham.
Yeah, so now we are going to show that this T alpha sigma, T beta sigma prime is not actually equal to 0 when we are in quantum theories. So we can always switch to holomorphic coordinates. So if we do that, there would be extra factor of 16. So that comes from the coordinate transformations. So there you have this T z z bar and T omega omega bars. So you have seen that these are the traces when you, I mean, in holomorphic coordinates, right? So let's start. So we need to start off with this conservation equation, which says the holomorphic derivative of T z z bar is equal to minus of anti-holomorphic derivative of TZZ. So now we can just square it up, multiply the equation with itself to get dz d omega acting on t z z bar t omega omega bar equal to del bar z bar and del bar omega omega bar acting on t z z t omega omega. Right now, this gives an equation for this stress OPE that we have had in this equation. Now on the right hand side, we have this TTOP, TZZ and T omega omega are the holomorphic components of the energy momentum tensor. So these doesn't vanish. So the leading order contributions of this OP would be C by 2 times C minus omega to the power 4, right? So that this now we need to solve this equation. We need to put this back in the previous equation and see what we get. So z minus omega to the power 4, we can break it up in derivatives. So that would be 2. We have written it in this way: del 2 z and del omega acting on z by 1 over z minus omega. Now there are previously anti-holomorphic derivatives were acting on it. So now we can take one of these anti-holomorphic derivatives and act on this z minus omega. This will go through these holomorphic derivatives. Now we know that there is a delta function identity which says delta of z bar acting on z minus omega is equal to delta function. So if we put this back in, we shall get that we have some derivatives of delta function on the right hand side. Is this clear? Okay. So we now we have our del z del omega acting on the stress of P, and we have del z2 del omega bar acting on the delta function. If we solve this equation and plug back the factors of C's, we shall get that this stress of P t z z bar t omega omega bar equal to C by 6 times pi del z del omega bar acting on this delta function. So that sort of says this is not exactly equal to 0, but there are some contact terms hanging around. So we can switch back to the previous coordinates in tau and sigma that will lead to T alpha alpha of sigma, T beta beta of sigma prime equal to C pi by 3 del 2 acting on these delta functions. Now we have this expression for stress OP now. We derived it using the conservation equation and delta function identity. Now if we plug this back here, take this expression of delta function identity and plug this back in, then we shall have two derivative acting on delta function, but we are integrating over the sigma prime. So the derivatives will be shifted to this function omega, right? So if we compute this, we shall get that delta T alpha alpha would be equal to C by 6 times del 2 omega.
Sorry.
And
Yeah.
yeah. Okay. So what was that? This omega was just the wild factor that shifts that measures the deviation from the flat spacetime, right? So if you write so this can be shown to be minus C by 12 times R. So if you compute R for a 2D background and then take the infinitesimal limit, then you will find it's just the d2 omega times some factor. So that is sort of, so this is the expression for slightly curved background, and if you write it in covariant fashion, it will just be the R, the Ricci scalar of the background. So that's the expression of Weyl anomaly for you. So and I am going to next mention a few comments without stating the proofs. So this is something that we have derived for the vacuum state, the expression of the anomaly. but it remains to be true for any other excited states. So this can be shown by creating excited states using path integrals by different boundary conditions. But you will still see that this delta T alpha alpha beta, delta T alpha alpha would always be R. That depends on the background and doesn't depend on the states. This is due to the fact that this arises, I mean, by regulating the short distance divergences, which is the universal property of the CFT, and doesn't depend anything on the states. And next thing that you can ask is why there is only C and not C bar. What's the what's special about the left moving central charges? So that can be answered. So when you couple a CFT to a curve space time, so it can be shown from consistency that we need C equal to C bar. So these conditions arises, so as Pratik was saying previously, this condition arises by demanding the cancellation of gravitational anomalies. So there are so you know that there are three order entities. So one that deals with the conservation equation and the symmetry of the energy momentum tensor. Those wide identities are in curve space time. Those are consequences of gauge symmetries. There are two types of anomalies in general. So there can be global symmetries and there can be gauge symmetries. The rule is one cannot just afford to have any anomaly corresponding to the gauge symmetries. So whatever appears on the right hand side of the equations has to just vanish. So if you restrict for consistency, so if you restrict the CFT on a fixed curve background, then this condition C equal to C bar will arise from there. So the answer basically is C by 12 times R equal to C bar by 12 times R. So there is nothing special about this left moving central charges. And this is the 2D and result. And in higher dimensions, you will have additional term and additional number. This is called A number. This is also like the central charge and appears the characteristic value of the CFTs. So this C is the Weil tensor and R is sort of the dual Riemann tensor. So this is far more complicated than 2D CFTs. This is just for information. So is there any question so far about anything, or I am going to move to the application that I was saying that will show.
So, like, what is this dual Riemann tensor?
Oh, this is just this you have to multiply it by some epsilons, I guess. Yeah. So R mu nu rho sigma hat would be equal to something R mu nu rho sigma multiplied by some epsilons.
Yeah, but the epsilon in 4 dimension will have 4 indices.
Yeah. So you will have some upstairs and downstairs indices. So suppose epsilon mu nu upstairs rho sigma downstairs multiplied by all downstairs Riemann tensors.
Okay.
Yeah. And you have to raise it using the metric for the upstairs indices. Yeah.
Yeah.
Okay. So okay. So while anomaly has a very interesting applications for 2D gravities. So let's see what is the problem that is associated with 2D gravity and how while anomaly solves this. But let's first discuss about few peculiar properties of these 2D gravitational theories. So we know that in D spacetime dimensions, the metric has d into d plus 1 by 2 number of degrees of freedom. Now you have d number of diffeomorphisms at your disposal, so you can use it to reduce this number further to d into d minus 1 by 2, which in d equal to 2 is just 1, right? So in 2 dimensions, all the dynamical informations of the manifold is entirely captured by 1 degree of freedom. So this becomes even more evident because in 2D it is always possible to choose a coordinate system in which you can write the g mu nu as e to the power sigma x times eta mu nu. So that means the all matrices are conformally flat in d equal to 2, and this while factor sigma captures all the dynamical informations. So you can of course write it down in holomorphic and anti-holomorphic coordinates as usual. That leaves us with only non-vanishing component of the z would be z bar, and that would be half e to the power omega. You can construct the inverse, and you can also show that the all the same indices of the Christopher symbol will survive. So that would be triple z and triple z bar, and most importantly the scalar curvature will be e to the power minus sigma dz bar times sigma. So both and holomorphic and anti-holomorphic derivative acting on sigma times e to the power minus sigma. So now that now what to describe the dynamics of this 2D gravity, we need an action for this wild factor sigma, right? So the usual choice would be the Einstein-Hilbert action, which is root over minus g times r. But the problem is in 2D that it integrates to a number that depends on the topology of the manifold only. So if you vary this with the wild factor, it doesn't stationarize, so it doesn't give rise to any action, any equations of motion. So the Einstein-Hilbert action in 2D doesn't really work. So there is a way out of this. So this was discovered by Polyakov in 80s. So the goal is we need an action for this wild factor sigma, because that captures all the dynamics, right? So what he did was he took some scalar fields or some other matter fields. It has to be a CFT, and coupled it to a curve spacetime, and then studied the response of the partition function with variations of this wild factor. So suppose we have two background matrices. One is G hat alpha beta, and other is G alpha beta, which are differed by this wild factor e to the power 2 omega x, right? So now we can study the variation of the partition function that lives on the infinitesimally, and then integrating that partition function, we can relate that these two partition functions on two different manifolds on that has this metric g hat and g separately, right? So if you vary the partition function, so you will get 1 over z del omega, that on the right hand side you shall get the variation of the action with respect to g hat, and the variation of the metric with respect to the wild factor. So that this product is going to end up being the trace of the energy momentum tensor, as we have seen above. Now we know that this if the matter field is a CFT, then this trace T alpha alpha is no longer will no longer vanish, but suffer from an anomaly, which is equal to minus C by 12 times R hat. I have added a extra term mu, so that would be the cosmological constant. So if you have zero cosmological constant, it will be flat space, and if you have some cosmological constant, then the energy momentum tensor on the right hand side would be shifted by a constant value, right? So that's so what we have on the Einstein's equation is just mu times g alpha beta on the right hand side if you have non-zero cosmological constant. So if you add this, it is sort of like the background energy, and if you add this, the trace of the energy momentum tensor would be also shifted by this value of the cosmological constant on top of whatever you have as the anomaly. So if you have a non-zero background energy, then T alpha alpha would be minus C by 12 times R plus this extra cosmological term. So if you now we can write the R hat. So if the matrices are conformally related, then the curvature will be related by this formula. R hat would be R minus 2 grad square acting on omega. So if you substitute the formula back in this, you shall get that you shall get an equation for del z del omega, right? So that would be minus c by 12 times root over g times this factor inside. Now we can integrate this equation to know how the partition functions on two different backgrounds would be related. So if we integrate this, we shall get z at g bar hat equal to z of z times this e to the power minus s, right? So this is the partition function that describes matter fields at a background g bar, and this is the partition function that matter fields that lives on z, and this is the missing piece that describes how the while factor would enter the action. So here we can see that although from the Einstein's equations we don't Einstein-Hilbert action, we don't have a kinetic term for the omega. Here we have. So here you have a del alpha omega del alpha omega term plus r phi term. So here, so this serves as a this action tells us about how the background will fluctuate at the response of the matter field that that we are considering. This action is famously called the Liouville action. So this is sort of the action for 2D gravity. I mean, this is sort of describes the dynamics of the Wild factor of the 2D gravities. So there is an exponential term here. So if we can switch off the background here. So we can set R equal to 0. Then we will be left with this kinetic term plus the potential term. So although there is an exponential term here, it can be shown that this theory is also classically conformally invariant. So one can check by computing the stress energy tensor, and it will have a zero trace again. So this is so far all the examples you have seen are the field theories, the CFTs are all the free theories. So this is a rare example of a CFT which has interactions. So yeah, so this is an example of interacting CFT. Okay, so that is all I wanted to say. If you have any questions or comments, please go ahead.
That was nice. Thank you, Shudipto. And I think, yeah, so if you guys have some things to ask, please go ahead. And I would actually, one more little thing that I would want you to do, Sudipta, is that try and see if you can set a couple of questions from here, because the I mean the algebra etc. was, I mean, as you know, was a little fast. So maybe if you can set some homework, then they might be able to just go through this in a bit, and they would be able to work out these steps, and actually that would be useful. So yeah, I mean, yeah, we can speak about it, and I've given them
Sure.
one homework which they're supposed to submit, I think, end of this week. So maybe just after that, we can give them another one, which is maybe at least parts of it can come from here.
Okay.
So are there questions for Sudipto? So here you essentially are seeing this term, this thing called an anomaly, which is the example of something which was a symmetry when it was classical, but when you have quantized the system, that symmetry may not stay. So that is the generic definition for anomalies. You have here seen an example of the wild anomaly, where wild anomaly or the trace anomaly, if you wish, where the trace of the energy momentum tensor in a conformal theory classically was equal to 0, but now you've seen that if you quantize the system, there it may not be 0. Actually, it is 0 only if the central term uh, of all the separate pieces of the whole CFT add up to 0, or if the background is flat. So it's C times R. So either C has to be 0 or R has to be 0. This is actually something that is very, crucial when we are doing string theory, and when there you also have CFTs. And so Sudipta mentioned this a little bit. There is a difference between, anomaly in something which is global symmetry versus an anomaly of something which is a gauge symmetry. Global anomalies are allowed. They can also have physical significances and so on and so forth. But remember that gauge theory is something that is formulated by us, and in the sense it's a redundancy that we put into the system, right? So it's something to do with the formalism of the system itself. So now if it turns out that the gauge symmetry itself, the symmetries become anomalous when you quantize the system, then there was something wrong in the formulation itself. So any time that you have a gauge anomaly, it just indicates that your system itself is sick. So gauge anomalies are something that we can't have. So anytime that you have, so if you find something that is a gauge anomaly, we just try and fix it in all ways that we can. And the fact that the fact this sort of links up with something else that many of you may have seen or heard, is that string theory is going to be consistent in only certain number of dimensions. You've heard the number 26, you've heard the number 10, and so on. That is to do with the fact where gauge anomalies actually become 0. It becomes 0 in these dimensions. Okay, so that's another point that I just wanted to stress a little bit on. And I think this particular thing about the wild anomaly is a nice thing to remember. And for those of you who are going ahead and trying to learn more about field theories and so on, you will be encountering anomalies everywhere. So remember this one as well. Okay, so I think we are. What's the time like? It's 2:49. Yeah, I think we can sort of wrap up. Sudipto, do you have something else to say, or should we just wrap up?
No, I don't have right now anything to say. So we need to set up an exercise for.
Yeah, we will do that. We'll do that in a bit. So there's no rush right away, but we will do that.
Okay.
So guys, no questions, I guess, right?
Sir, I have a question.
Yeah, please go ahead. Yes, please.
Sir, there was an omega.
Oh, okay. So let me share again.
Hello.
Sir,
You are a little on and off. So could you ask what you were saying once more, please?
sir,
I'm sorry, we don't hear you too well.
delta G.
We don't hear you too well. Could you repeat once more? I'm sorry about that. This internet
Sir,
is, yeah, please go ahead.
um,
Which slide? You don't have any slide numbers,
uh,
Shudipto. Should he go up, down? Yeah, I think down.
sir, there was something like the end of the.
At the end,
Um,
should he still be going up?
So what is this about? Is it about deriving the anomaly, or is it about the Liouville theories?
actually, I have a question about that.
Okay.
I think she is
As,
actually,
as soon as she's trying to ask the question,
yeah, it's going off. It's, yeah. Last time around, there was such trouble with my internet. I've bought a heavy duty router now. Now I have a heavy duty router which I set up just before the class today. Yeah, I think she dropped off. Hopefully, if you can hear us, I think that was Minu, right?
Yes, sir.
So
Sir,
yeah,
there was.
yeah. The moment you start to ask anything, Minu, I'm sorry, your voice just goes off. Maybe you can. Yeah, we will share this as well. It'll be on the, I mean, on the website. Maybe you can point out where exactly you had the issue and send us an email, and then we can address this. Is that okay? I'm sorry for this internet trouble. This is
Mhm.
really irritating. But uh, yeah, I think Shoykot, I know she can, but if it's an equation and if it's long, trying to write it down out here, it may be difficult. Minu, you could try and write down a little bit if you want an answer right away. If we could at least figure out which equation you are interested in, we could go there and maybe explain a little bit more. Yeah, anyway, so let's maybe so if there are any other questions, I think we are happy to try and address them, modulo internet problems, of course. Doesn't seem to be the only question that we had. Unfortunately, we didn't get through because of our internet problems. Anyway, I think we are done for the moment. And Shudipto, could you please send me your files as well? Oh, Omega.
yes, yes.
Is Omega restricted or not? Okay, so Shudipto, I think the answer is, yeah. So she's asking if I think the Omega that you write down is probably not this one, but the next one where, no, I mean, I think at the end, yeah. No, this is a sigma, right?
Yeah.
This is a sigma. Then the omega is above, I guess. So this particular, I mean, omega, if you're asking about the thing about the thing with the trace, this is just, yeah, infinitesimal yeah, infinitesimal deformations from flat space. Do we have you actually written this down somewhere, Sudipta?
Yeah. So
Where was it?
how the
What exactly? Yeah, there are too many omegas around everywhere.
yeah
Have you written down how the coordinate
yeah
depends?
so
Yeah,
so so
this is the
that's
omega. Yeah.
yeah
But this is supposed to be flat space. So these g's that you have, uh,
on the right hand side would be eta.
right hand side would be eta. Yes. So this is an infinitesimal deformation away from flat space. Think of this exponential as being expanded, uh, and you've kept 1 plus the I mean 1 plus 2 omega out there, and the thing that you have is flat space. Okay, so g is 1 plus twice omega into eta beta gamma. So that's what you would actually start off with. Yeah, so maybe, yeah, okay. So that's what it is. So there are no restrictions on this except for the fact that this is small. It's just small, I mean, small deformations away from flat space. Does that answer what you were saying, what you were asking? Okay. Hopefully we have been able to get through. If not, yeah, if there are anything, if there's anything else, please feel free to drop us an email. Okay. All right then. All right, so I'll stop recording and